maybe a little low. The first one. Thank you everyone for attending this presentation. I'll be talking on behalf of my co-authors, Domenico, who was a visiting student from Politecnico Milano, and rest of us are from Leuven and EnergyVille in Belgium. So there is a impeding problem of lack of quality of data set, and that's the motivation that we have. We are looking into data sets for consumer load profiles, EV charging profiles, and PV generation. And so the scarcity of representative load profiles makes the study in distribution network operation and planning context very hard. And there is an additional problem of scenario generation, which needs to be realistic. And with this motivation in mind, we analyzed 3 publicly available data sets for quantifying seasonal and annual uncertainty for efficient scenario creation. And in this pursuit, we look into 3 data sets from the Netherlands and in Belgium. So Elaad provides the EV charging profiles. Elia and Fluvius are also gathering load profiles, which we'll be talking about subsequently. And we utilize these and perform and statistically analyze to create more better insights. So the first data set is from Netherlands. Of course, these slides are also online, so you can use these QR code also to directly download them. The second is for PV profile, which is from Elia. Elia is a TSO in Belgium. And third data set is from the consumer load profiles, which is provided by Fluvius earlier this year. It launched 1300 load profiles for which we'll be talking about in the slides. So moving on to the first data set, which is the electric vehicle charging profiles. So there are 10,000 charging events, which in this data set that we have. So it's provided by Elaad. Elaad is a very unique initiative by the Dutch grid operators, which has the aim to scale and consider the implications of large-scale EV integration into the grid, while also facilitating smart charging. So for this data set, the power ranges were from small scale to high, which is 23 kilowatt, and the maximum charged energy is exceeding 80 kilowatts hour. So the uncertainties identified here for this data set is the arrival time, departure time, charge time, the peak power, and the charged energy. And the distribution of these attributes are here. Yes. So the first plot shows the arrival time. The second plot shows the conditional probability of the departure time with respect to the arrival time. And then subsequently we have the connection time. So normally the EVs are connected for longer period of time compared to the duration in which they are actually getting charged. So that's the moment of extraction of flexibility, because that will be allowing us to move our electrical load in temporal aspect. And the final plot here shows the charged energy with respect to the peak power. Although majority of the charging sessions were small charging sessions for 0 to 10 kilowatt hour, but there are substantial number of higher power charging sessions. And for scenario generation, we provide like a sequential method in which we sample the arrival time, then we look into the conditional probability of departure time once we fix the arrival time, and so on. So these are the 4 steps, and the final scenario which is generated consists of these 6 attributes, which is the arrival time, departure time, the connection time, the peak charging time, the electrical energy which actually is charged, and the charging duration. And this is based on the randomized selection, which is based on roulette wheel selection method. With this, I'll move into the second data set, which is PV generation profiles. I would like to highlight here, so whenever we do a forecasting, it's very crucial at what time scales we are doing. So what we are showing here is the PV generation forecast in the hour ahead, day ahead, and the week ahead cases. And we see these forecasts incrementally get worse as we have look ahead, and these factors are somewhere around, on average, 4 to 8 times getting worse compared to hour ahead. And you can see there is a seasonal implication. So normally the PV profiles are very easy to predict during January or December when there is no actual sun. So the errors are very low, which you will see in the next slide. So this is the normalized PV generation in Belgium. So the dark black line shows the mean PV generation, and from this plot of distribution, so the lighter shades of red shows the probability is lighter, lesser. The chances of happening is low. So this is a fan plot. So we can see that only for 6 months, from March to August, it's actually the peak is reaching 70% of its rated capacity. So with these distribution, we can actually create scenarios, which is described here, three-step process. So the first step is the seasonal variations can be captured with the distribution of the PV generation. Uh, PV size can be selected. So this is the second uncoupled uncertainty. It can be 3 kilowatt peak or 10 kilowatt peak. And then there is another uncertainty which needs to be studied further. And I think there is a lot of missing literature. There is PV installation geometry, like what tilt the PV angle is, and so on. And this will create the solar generation profile. Finally, moving into the last data set, the consumer load profiles is based on the recently launched by Fluvius, which is the DSO in Flanders, 1,300 Belgian electricity consumers. And for this data set, which is pretty high quality with no missing data, and timestamps are correct, which is actually very hard to find. So 5 types of consumers can be classified based on whether they have EV, PV, or heat pump or not. So at the end, you can see the number of consumer profiles for a whole year that we have for that particular consumer type of consumer. So just to give you a visual idea, so type 1 consumer which has no EV and PV has a load profile approximately which never goes to zero, never becomes negative because there is no source of distributed generation at the end. However, type 2, type 4 and 5 which has PV visually can be seen that they have certain amount of reverse power flow happening. So what we do is we create these, for each of these consumers, we try to study attributes and gather and create metadata. Like when are the peaks happening? What is the distribution of peaks? In which month and what time period are these peaks happening in the direct flow and the reverse power flow? So these can be accessed. This is also in the repository, which I'll be talking about subsequently. I don't want to go into the table here, but yeah, feel free to access the paper and the presentation online. So I would like to end my presentation with 2 takeaways. The first is we analyzed 3 publicly available data sets for quantifying seasonal and annual uncertainty, which is Elaad for electric vehicle, Elia for PV generation, and Fluvius dataset for consumer load profiles. And the second is we provide a skeleton of a scenario generation for PV and EV profiles in the form which has been discussed previously. And finally, which might be very useful for many of you, is this open repository, which has all the data sets for EV charging, PV generation, load profile. So just to give you a context that it's not directly picking up the load profiles from their website and not doing any post processing. What we do here is, for example, the load profiles provided by Fluvius were more than 3 GBs of one Excel file. It's impossible to do detailed analysis without breaking it into several parts. So what we did is we compressed the data into subsequent files for efficient scenario creation and performing evaluation on the data set. There is one more thing that we did in the presentation, since the bell is not here. I would like to talk that we also were measuring weather data in Belgium. So what we did is we selected some representative days in which all these peaks and dips are happening, the worst cases. So although there is a slide in between, I'll jump into this. So we measured a lot of these things like solar insolation, wind speed, temperature, and so on, and tried to find a correlation between these peaks and dips happening. Although this is an ongoing work, have not been subsequently uh, concluded in this paper, but I think this is an interesting direction in which we can show causality with network uncertain variables and how that implicates or impacts our consumption behavior. Maybe not all the load profiles are getting directly correlated with certain attributes or certain weather parameters, but I think there is a lot to dig in this direction. Thank you.
Thank you very much. It was on time, and you shared really good information with the QR codes in there as well.
Yeah. The presentation is also online, so I already put it. So if you search with the paper name, I think you should find it. Because we had a lot of students and everyone had this question, which load profile to select and which network to select. I think the network paper will be coming as a general paper subsequently.
Great. Questions?
And are the consumers, are the domestic consumers or like the commercial, like shopping malls? No, all of them are domestic consumers, but these consumers are drastically different from each other because if you see the peaks, it's so these are the distribution. So what it shows is like what is the kilowatt. So this is the power and that's the energy. So all the consumers are reflected in the first plot. So you can see they have a huge difference. Like what is the maximum kilowatt and what is the maximum energy that they are consuming. So there is a very wide behavior. So but all these consumers are domestic. Maybe some of them are larger than others, but all of them are low voltage consumers. Also the fact that you put like the plug-in time is more than the actual charging time, right? Yes, because that's the flexibility. Yeah. So EV load is not flexible whole of it, right? It's flexible by certain temporal deviations, and that deviation is coming from what is the difference between my connection time. Like if I'm standing my car at 5 hours and I'm charging only 4 hours, then 1 hour is the flexibility that I have, not 5 hours. Yeah. So I think that needs to be clearly understood.
So since we have a little bit of time, I have a question. In your experience, you've seen this data. Currently, grid operators have a lot of concern about this new load that is coming. Um, how is it going to be possible to optimize, when you face up with a lot of EVs connecting probably at the same time?
Yes. So these are future studies such as like hosting capacity studies. So we want to see like how much hosting capacity of a network for a particular DER, which can include EV, PV, heat pump. Heat pump may not be a reality in many parts of the world, such as Australia, but I think it's very common and growing drastically, much faster than EV in Central Europe. So the heat pump load is expected to be much problematic because they are simultaneous in nature. They are highly correlated with temperature variations. EV is still there are sharp peaks, so I think that's a big problem. Many of the DSOs don't even have uh, the information that how much DERs are connected. Maybe for PV they have because of the reverse power flow that they can detect, but for EV I think it's very easy to hide. I'll give you an example of Belgium. So system operators charge like 1,500 euros to perform a feasibility study in Belgium in order to allow you to connect a EV, right? And it's an incentive for the consumers to not reveal that whether they have an EV or not, which is making it very difficult because these peaks are happening all of a sudden, and they have a embedded simultaneity because everyone comes from office around the same time and they connect the charger. I think this is a big problem.
Thank you. Thank you very much.
Thank you.
We have one more question.
Sure.
If we can be quick, please.
Sorry for a late question. Thank you for the nice presentation. My question is related to demand side management.
Yes.
We are moving towards smart grid. So is this load somehow considered the demand side management issues that have been practiced in Europe or somewhat practiced, or even in future, do you consider demand side management as an uncertainty factor?
Yeah. I think so. Of course, there might be something. Maybe some of the people have home energy management system, but I mean, we are already thankful to the DSO to have this. Now, in order, they also don't know. This is the problem. It's not like they know and they are not telling us. We don't have enough information on what's happening in the house if there is a home energy management system. And I think how the market design is happening presently is going to be very problematic if they don't have a locational aspect to it in near future because we are not considering the simultaneous behavior of consumers, which would be more problematic because just consider time of use prices. If you are responding and there are 10 other consumers in the same feed are responding, it might be more problematic than actually we would call the present as a good days because randomization and inelasticity of consumers towards electricity prices. That's my opinion. I think, but I don't know if there is uh, local intelligence in controlling loads, possibly, but I would not say at a very large scale.
Okay, thank you very much.